All right, so we're starting chapter 12, which is probability. This is great for standardized tests. They love to ask questions on probability. Okay. We're going to learn today about sample space and then general probability, and then we're going to get more specific as the chapter continues. So some vocab terminology on this slide. The first is the probability experiment, which is an action or trial that has varying results.
Like a science experiment?
No, but it would be probability. So like the chances of blank. Right? Like
Chances of me dying?
sure, that would be probability. Yes.
Chances of school exploding?
Yeah, I'm sure there's probability that could be done on that too.
Rolling a 17 on a 27
Yeah.
die.
Yeah.
Chances of
Okay. All right. It's very doomsday of you guys. All right. The outcome is the possible result, like being blown up or not being blown up. Okay. But more lightly, like maybe if you're rolling a die, there are 6 sides, then the outcomes are 1, 2, 3, 4, 5, or 6. Like what is the possible end result? If you are flipping a coin, then it is flipping a tail or heads. Yes.
Will this lesson make me a better gambler?
I don't know. Depends on how good you are right now. All right. Then the event is an outcome or collection of outcomes. So something specific like what you want to happen. This is like your goal here. What you're hoping the outcome is. For example, rolling an even number. Not blowing up, I would say, is what we want. That would be the event. And then the sample space is the set of all possible outcomes. So if you're rolling that 6-sided die, then the possible outcomes are 1, 2, 3, 4, 5, 6. If you're pulling a card out of the deck of cards, you would have to, which is one of the things you're going to have to familiarize yourself with, is the deck of cards. The sample space is all those possible outcomes. Example 1 says A, you flip a coin. So that's the event. You're flipping the coin twice. How many possible outcomes are in the sample space? List the possible outcomes. So if you're flipping the coin twice, how many, like if you wanted to do the number of options without actually going through the possible outcomes, because that's 2 different questions, then you would just figure out how many times, like how many options there are the first time you flip the coin, how many options there are the second time you flip the coin. So the first time there's how many options?
2.
There's 2 outcomes. And the second time there's 2 outcomes. So there'd be 4 possible outcomes if there's 2 events and each event has 2 options. Okay? If you want to list the actual outcomes, then you could flip the coin and you could get tails twice. You could land on heads twice. You could land on tails and heads, and you can land on heads and tails. So you're doing the coin twice.
So basically, multiplying it by 2 gives us the other 2 outcomes.
Right. So if you are, go to the next one. If you flip a coin and you roll a number cube, how many possible outcomes are there? And then list the possible outcomes. So think about the how many first. If you're flipping a coin, this would be the first spot. And then you're rolling a number cube, that's the second spot. How many outcomes are there in the coin?
2.
2. How many on a number cube?
6.
So the possible number of outcomes here is what? 12. Now we got to figure out what they are.
Wait, are we going to list all?
Yup.
No way.
Yes way.
Should I do this on the test?
The possible outcome, I mean, we're going to get to very different kinds of questions by then. But how many options? Certainly. Okay, so if I flip, let's say I land on heads the first time, it could be heads with a 1, with a 2, with a 3, with a 4, with a 5, and with a 6. And then I could have landed on tails the first time. So tails with a 1, tails with a 2, tails with a 3, tails with a 4, tails with a 5, and tails with a 6. Those are your possible outcomes. And there are 12 of them, so it should match up with what we found. Good so far? All right, the probability, so that's the sample space and the number of outcomes. The probability of an event is the chance or likelihood the event will occur. So you're talking about either a 0.25 or a 1/4 or a 25%. So it can be written as a fraction, as a decimal, or as a percent. It has to be between 0 and 1. If it was less than 0 or even 0, it's impossible. And if it's bigger than 1 or equal to 1, then it's certain. So it has to be in between those two. The notation for the probability of an event, so if we're saying the probability of event A occurring, then it will be written as P with the parentheses of A. If it was probability of event B, then I would just do P parentheses B. And this is just your scale. Obviously, if it's at 0, it's impossible. If it's at 1, it's certain. Halfway between like flipping of a coin. If it's not a weighted coin, we're assuming it's a fair toss-up, okay? Then it's 50% likely to occur, or 0.5 or 1/2. Theoretical probability can be found when all the outcomes are equally likely to occur. So like I just said, we're assuming that it's not like nobody's cheating on these things, okay? It's not a weighted coin. It's not a rigged lotto, that kind of thing. It is a fair probability. And to find that, you do the number of favorable outcomes, so what you want, over the total number of outcomes.
AKA what you want to get over total.
Correct. And again, it could be a fraction, it could be a decimal, it could be percent. Usually it's fraction or decimal, like unless it says percent. All right, example 2 says you toss a coin and roll a number cube. What's the probability that the coin shows heads and the number of the cube shows 5? So think about what we already went through all of these. It was H1, H2, H3, H4, H5, H6, and then it was T1, T2, T3, T4, T5, T6. So how many of those is what we want? A heads with a 5.
One of them.
There's only one of them. So there's one that we want. And the total number is 12. So you leave it just like that. Correct. Yeah. Why what? Because it was two things. It was flipping a coin and rolling a die. So the outcomes are you can flip and land on heads with a 1, with a 2, with a 3, with a 4, with a 5, or with a 6. Or you could flip and land on tails and get a 1, a 2, a 3, a 4, a 5, a 6. So there was 12 outcomes. B says, what's the probability that a student chooses a t-shirt with a gold emblem? So now you're dealing with a chart. This is what like ACT loves charts, okay? But a lot of standardized tests love stuff like this. The probability a student chooses a t-shirt with a gold emblem, and it's not saying a green t-shirt with a gold emblem, it's saying, or red, it's saying just the gold emblem. So I'm gonna take and I'm gonna add together every time somebody chose a gold emblem, which was how many? 16 over the total amount. This was 16, this is 14. So the total amount of kids that answered this survey, which is 30. And then we always simplify what goes into both 16 and 30. 2, it would be 8 over 15. Huh? No, we didn't need to list anything. Usually the charts are a little bit easier. Just got to figure out what it's asking for. Questions on that one? All right, probability of the complement of an event. So sometimes it is more likely not to get what you want than it is to get what you want. And sometimes it's easier to count the what you don't want, okay? So that's when you would use the probability of a complement. The complement just is 1 minus the probability of the actual event. So if my chances of getting an event are 1 in 12, the complement would be 11 over 12. You would do 1 minus whatever the probability of that event is. So if it gives it to us in decimal, like this, and it says this little P over with a bar over the A, that means complement. Okay, sometimes they call it P hat. If I want to find the complement to that, then I literally just do 1. So if it's 1 minus 0.45, what's the probability of the complement of this activity? 0.55, right?
Wait. Oh, okay.
Yeah?
I thought it'd be 1.45.
So it's
It'd be 1 minus 0.45.
so
The complements you're looking for here. So if the probability is 0.45, then the complement to that would be 1 minus that, which is 0.55.
it's equal.
Not
I guess
equal.
equally to have and equally to not have.
No, 0.55 is, it's more likely that you don't get what you want here, right? 0.45, it's, I mean, just a smidge less. But if you want it, if whatever A is that you're trying to get, you are less likely to get that than to not get it. That's what the kind of tells you.
I thought you meant the complement.
If I said, what's the probability, like if I go back to that last example, and I said, what's the probability of not getting, what was it, a 5 and heads, then I would do 1 minus that 1 over 12, which is 12 twelfths minus 1 12th, or 11 twelfths. So if the probability is to not land on that one, you could figure out what the probability is to land on that one, and then I would subtract it from 1, or in this case, 12 twelfths. All right, geometric probabilities. So these can be found by calculating a ratio of 2 lengths, 2 areas, 2 volumes. And again, you would be putting what you want to land on, so whatever you want, over the total, either area, length, whatever it is. So in this example, it says you throw a dart at the board shown. Your dart is equally likely to hit any point inside the square board. Are you more likely to get 10 points or 0 points?
0.
Well, we got to figure it out. So I'm going to try to figure out what's the probability of getting 10 points and then the probability of getting 0 points, and then I'm going to compare them. So the probability of getting 10 points is in this little circle. Obviously, we're talking about area here, right? So I'm going to get the area of the pink circle, and I'm going to put it over the area of the square, the whole shape. If I want to get 0 points, then it's the blue. So it's the area of the blue section over the area of the square. How do I find the area of the pink? How do you find the area of that pink circle? Pi r squared, and r is what? 3. So each of those little segments is 3. That's what that 3 with the arrow means. So the area there would be 3 squared pi, or 9 pi. And the area of the overall square, how do I find that?
I think it's 9, not 9.
So it's, this is 3, this is 3, this is 3, right? Which means that's half my side length would be 9. Good, the whole side length would be 18. And this would be 18 squared. 18 times 18. 324. So these you'll most likely answer. It probably will. I mean, if it said keep it exact, then it would be that. Actually, you can reduce that, right? 3 plus 2 is 5 plus. Yeah, we can reduce that because 3 goes into both of them. This would be 3/108. So I could do 3 pi over 108, and then that gets reduced again. 1/36. So this is pi over 36. But if I'm going to compare it to something else that's not going to have pi in it, well, it could have pi in it, but it might not be exact, then I want to actually find the decimal there. So I'm going to take pi, and I'm going to divide it by 36 and get a decimal. The whole goal here is to compare these at the end. So I could have done it from the beginning. I could have done 9 pi divided by 329. Or pi divided by 36. And that's 0.087. Now I go to the area of the blue section. How do I find the area of the blue section? Good, so I'm going to do the total area of the square, right? Minus what? What do I have to take away? The yellow, green, and pink circles, right? So it would be all the way across, which has a radius of what? 9. That area would be? Good. Circle. So the area of the square we just found was 324 minus the area of the circle, 81 pi. That's just the area of the blue part. So that's my numerator. And then we're going to put that over the area of the square, which is 324. And then I'm going to do all that in the calculator. 324 minus 81 pi divided by 324. And I get 0.2146 and so on and so forth.
Wait, what did you do?
I did so for the top, I took the area of the whole square and I subtracted from it the circle.
Okay.
And that gave me the blue part. And then I put it over the area of the whole thing, which is the square. So which one is more likely to happen? 10 points or 0 points? 0 points, because that is higher probability.
Is like drawn to scale? Like I could just see it if I get 0 points.
You don't want to ever assume it's drawn to scale, but sure. I mean, like if it's 333 there, it's pretty accurate. It doesn't necessarily mean it would be 3 inches, but it could be the same measurement on each of those segments. Yeah.
You subtracted the square from what?
No, I did the square minus the circle, and that gives you the blue part. That's in the numerator, and then I put it over the whole thing, which is the area of the square. All right, experimental probability is based on repeated trials of an experiment. So you're doing the same experiment over and over again. The number of trials is the number of times the experiment is performed. So if I'm rolling the die 3 times, if I'm rolling the die once, rolling the die twice, rolling the die 3 times, then 3 is the number of trials. Success is each trial in which a favorable outcome occurs. So if I'm rolling the die and I want to land on a 2, every time I land on a 2, that is success. And experimental probability is found by doing the number of successes over the number of trials. All right, so example 5 says each section of the spinner shown has the same area. The spinner was spun 20 times. The table shows the results. For which color is the experimental probability of stopping on the color the same as the theoretical probability? So theoretical means look at your original spinner. What are the chances of rolling blue? 1 in 4. What is the chances in rolling yellow? 1 in 4. Red. 1 in 4. Green. 1 in 4. That's the theoretical probability. The experimental probability is this actual outcome. So how many times was it actually spun? 20. So this would be 5 over 20, 9 over 20, 3 over 20, 3 over 20, and you're looking for where they're the same. 5 over 20 reduces to 1/4, so red is where they occur the same. So theoretical is what it should be if it's fair and even, and then your actual experimental is what happened. So that's based on data. Yeah, sure.
Which one is the picture? Experimental?
The picture is theoretical. Experimental is what actually happened after you did it.
So theoretical is what's supposed to happen
Correct.
in the perfect world.
Correct. Okay, so 2 important things, I think. All right, so 2 important things that your book or standardized tests assume you know just from being alive. And that is what a deck of 52 cards looks like. And the other is something, well, you don't have to know this, but these little, this drawing, I don't know why it's duplicated actually. I can crop this. All right, the other is the outcome of rolling 2 die. So, and the top things you need to know about cards are that there's obviously 52 of them, thus 52 card pickup, right? There's 52 total cards. Half are red and half are black. So 26 red, 26 black. There are 4 suits. They are hearts, clubs, spades. Actually, I should have gone in a different order. Diamonds, hearts and diamonds are red. Clubs and spades are black. Huh? Okay. Clovers. That's a club. Yeah. So there's 13 of each. So it might ask you, like, what's the first of all, the sample set would be 52 cards, but what's the probability of drawing a black card? It is 26 out of 52 or 1/2. What's the probability of pulling a heart? It's 13 out of 52 or 1/4, okay? The other thing you have to know is a face card. Do you know what a face card is? What distinguishes a face card? It literally has a face on it. So people tend to think that like 10s count as face cards. They do not. Aces do not count as face cards, right? Okay. They literally have a face on them. So just Jack, Queen, and King are called face cards. Okay. If it does something where it talks about like high or low, like if it says the probability of getting something greater than 8, it will indicate what the other ones are. Is ace high, is ace low, that kind of thing. You got to wait till she comes back. Questions on the deck of cards? Okay. It does not include jokers, nothing like that. The second thing is this is the result of rolling 2 die. So when you roll 2 die, you can roll a 1 with a 1, a 1 with a 2, a 1 with a 3, a 1 with a 4, a 1 with a 5, like all the way down. And so this is like a probability question might come up with it. What's the probability of the sum of the die being blank? Okay, and that's what all this is. All the stuff inside here is what you would get if you would add those 2 die up. So a 1 with a 1 is 2, a 1 with a 2 is 3, that kind of thing. You don't want to have to draw this out every time and try to figure it out. So if you can understand the pattern, it helps, okay? But it would, so like if it's saying what are the chances, first of all, if it said rolling a 6, what's your overall sample space? If you roll 1 die, it's how many? 6. If you roll it again, it's how many? 6. So how many different outcomes are there? 36 if you roll it twice. So my total is going to be 36. If I counted these boxes, it's 36. Okay. How many of these boxes have a 6 on them? 5. So the probability of rolling a 6 is 5 out of 36. Okay. The probability of rolling a 7 is 6 out of 36 or 1/6. Okay. So that's where this little box will come in handy instead of having to try to literally figure out your combinations.